Here are the 6 items we want to investigate using our simulation of the Bohr model. Number 1 is when no light shines, the electron remains in the smallest orbit. An electron in its smallest orbit is in its ground state. And later we will learn when the electron is hit by a photon and absorbs a photon, it is lifted into an excited state. The second observation is we select light as a wave with a wavelength, for instance, lambda equals 6.56 nanometers, but our light gun shoots a particle at the atom. Yes, light is both a wave and a particle. This is called wave-particle duality. A duality is 2 pictures of the same thing. It is a wave and a particle. Duality means an object has 2 characteristics at the same time. Your duality is you are a son and a brother. This is one of the most astounding and perplexing phenomenon in physics. And it is a good idea to think about very carefully what it means that something can be a wave and a particle at the same time. So please repeat after me: wave-particle duality of light. To see how a wave looks like, we use a simulation from the University of Colorado, PHET. The simulation is called quantum wave interference, and we click here on this, and here you see a typical example of a wave. So this is a wave. Here we draw a wave which is very idealized, and you can see that there is a wavelength and also the height, which is called the amplitude. And the most important thing is that a wave is continuous. It can be simultaneously at many points in space. That's a wave. On the other hand, you have a particle, and a particle is always discrete. That means it is 1, 2, 3, and it can be at only one point in space at a time. And here is how particles look like. They are discrete. You can count them. 1, 2, 3, 4. They are at one point in space at the same time. They cannot be at several points at the same time. This is the great difference between a wave and a particle. If you think it is difficult to imagine light as a wave and a particle at the same time, don't be disappointed or don't be discouraged. Great physicists had the same problem. One physicist is quoted as saying, when he heard for the first time that a wave and a particle has a duality, so something can be a wave and a particle at the same time, he said, with the left eye, I close the right eye, and with the left eye I see a wave, and then I close the left eye and look with the right eye, and I see a particle. And if I open 2 eyes, I become crazy. But it turns out that sometimes it is more useful to view light as a wave, and sometimes it is more useful to view light as a particle. For instance, when you want to study how light travels through space, it is best to look at light as a wave. A wave is identified by its amplitude A and its wavelength lambda. Lambda is Greek for L, small l. And here you see a wave with the amplitude A and the length is lambda. And one cycle of the wave has the length of lambda, and we measure the length, of course, in meter. And the time it takes to complete one cycle is labeled with the letter capital T. Here you see the spectrum of visible light, which starts a little bit below 400 and extends above 700. And if you go beyond that, you go into the light that is not visible to humans. On the right-hand side, it is infrared. And you have also a spectrum on the left-hand side far below the 400 nanometer, which is also not visible to humans, which is called ultraviolet light. And you know that when it is very hot in summer, protect yourself against the sun, because the ultraviolet light can damage your skin and might cause skin cancer. So the low wavelength of light starts for the more violet light, then it goes into the bluish, greenish in the 500, yellowish in the 600, and in the 700 it is in the red range. For instance, red light, which is absorbed by the hydrogen atom, has 656 nanometers, and nanometer is abbreviated as nm, which is equal to 10 to the power of minus 9 meter. 10 to the power of minus 9 meter. We want to answer now two questions. Number one, how many cycles of light, each with a wavelength lambda equals 656 nanometer, occur per second? And the second question is, how many seconds does it take for light with a wavelength of lambda equals 656 nanometer to complete one cycle? Here is what we need to know. First, the wavelength of red light absorbed and emitted by the hydrogen atom, lambda is equal 656 nanometers. Now we know that a nanometer is 1 multiplied by 10 to the power of minus 9 meter. Therefore, 656 nanometer is equal to 656 multiplied by 10 to the power of minus 9 meter. And 656 multiplied by 10 to the power of minus 9 meter is the same as 6.56 multiplied by 10 to the power of minus 7 meter. We break the steps down how to transform 10 to the power of minus 9 to 10 to the power of minus 7, in case you have some problems with this. But what it boils down to is, it is dividing multiplying and dividing the numbers by 100, which means essentially 100 divided by 100 is equal to 1, which does not change the value. Please stop the video here and go through this example line by line. The second fact we have to know is, how fast does light travel in 1 second? And of course, light travels at the speed of light c, and c is equal to 300,000 kilometer per second, which is the same as 300 million meter per second, which is equal to 3 multiplied by 10 to the power of 8 meter per second. So the question we are asking is, how many cycles does it take for light of wavelengths lambda equals 656 multiplied by 10 to the power of minus 9 meter to travel 3 multiplied by 10 to the power of 8 meter? When you think about it, a similar question would be, how many steps of 0.4 meter lengths does it take to walk 1,000 meter? Consider one step, the wavelengths, and the total distance you have to travel is 3 multiplied by 10 to the power of 8 meter. We make this calculation in 3 steps. The first step is 6.56 multiplied by 10 to the power of minus 7 meter takes 1 cycle. 1 meter takes 1 divided by 656 10 to the power of minus 7 cycles. And 3 multiplied by 10 to the power of 8 meter takes 3 multiplied by 10 to the power of 8 divided by 656 multiplied by 10 to the power of minus 7. And this tells us that for that light to travel the distance of 3 multiplied by 10 to the power of 8 takes 4.57 multiplied by 10 to the power of 14 cycles. In this calculation, you should always separate the significant digits, which are the red ones here, 3 and divided by 656, and the blue number, which we call here the exponentiation, and calculate them separately. The number of cycles per second of light is called frequency of oscillation, or simply frequency, and the letter that is used is the small Greek letter for n, which is nu, pronounced nu, and this is the Greek letter of n. And the unit for frequency is hertz, that is the number of oscillations per second. So 1 hertz is 1 frequency per second. Given the wavelengths and the speed of light c, the light's frequency is calculated as nu equals c divided by lambda. This is exactly what we did in our calculation. We divided the speed of light c by the wavelength lambda, and that gave us the frequency nu. And of course, simple arithmetic tells us that the speed of light c is equal to the frequency multiplied by the wavelength lambda, and the unit is meter per second. So we have found that light with a wavelength lambda equals 656 nanometer requires 4.57 multiplied by 10 to the power of 14 cycles to travel 3 multiplied by 10 to the power of 8 meter in 1 second. That means light with a wavelength lambda equals 656 nanometer has the frequency nu equals 4.57 multiplied by 10 to the power of 14 hertz. And just to check whether we got this right, we plug in the numbers into the equation c equals lambda multiplied by nu, and this seems correct. Now we can easily answer the second question. How many seconds does it take for light with a wavelength of lambda equals 656 nanometer to complete one cycle? In other words, what is time t, capital T, for lambda equals 656 nanometer? And we do it again in 3 steps. The first step is 3 multiplied by 10 to the power of 8 meter is traveled in 1 second. 1 meter is traveled in 1 divided by 3 multiplied by 10 to the power of 8. And number 3, 656 multiplied by 10 to the power of minus 9 meter is traveled using this expression here. In the numerator, you have 656 multiplied by 10 to the power of minus 9. And in the denominator, you have 3 multiplied by 10 to the power of 8. And we do this calculation here, and the result is for light with a wavelength of lambda equals 656 nanometer, it takes 2.18 multiplied by 10 to the power of minus 15 second to complete one cycle.